Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 1, we want to talk about wave motion, which is one part of the oscillatory motion. So, if you want more of these videos, please consider subscribing, and also the lecture notes will be in the description below. So, we should just go and start by actually discussing about waves. So, what are waves? So waves are basically a disturbance in a medium such that you don't actually transmit the matter, but instead you transmit its energy. So for example, if you have, like, for example, a spring, no, sorry, something like a slinky, and then you give a sudden impulse, there will later be a propagation in in the in the medium that causes energy to go from one place to the other without transmitting its matter. And so that is what we call as a wave. So for today's videos, we want to talk about mechanical waves. Mechanical waves are waves that is caused by mechanics. So there won't be any electrostatic, there won't be any magnetic, and etc. We will only deal with objects moving. So there are two kinds of waves that I want to discuss. One of them is a longitudinal, while the other one is long longi longitudinal. Tudinal. Tudinal. Okay, there we go. Longitudinal as well as a transverse wave. So what is the difference? So for a longitudinal wave, the displacement is parallel to the propagation of the wave. So let's just state that if you have the wave propagating in this direction, that means that the wave matters are moving in the longitudinal direction, or to the parallel to the propagation of the wave. So you can see here that the density is much more tighter, and then there's some which is less dense. So that's one of the properties of a longitudinal wave. The other one is a transverse wave. So a transverse wave is if the displacement is perpendicular to the propagation of the wave. So so this is one of the examples of such. You have you have a string going up and down. So basically the displacement goes up and down. So this is a transverse wave. So there are some things that I want to discuss about how do you actually describe a wave. So first of all, we have something which we call as a amplitude. So like last video, amplitude is basically the maximum displacement. And then after that, I want to talk about different kinds of wave. So the way that you actually describe the shape of the wave is something which you call as the waveform. This is the shape. And there are multiple different types of waveforms. One of them is a pulse. The pulse is basically you only give it only one input, which is isolated. Another one is a continuous wave. A continuous wave is when you actually give it a if you give it a propagation which is periodic. That is what you call as a continuous wave. And then there is something which we call as a wave train. So what is a wave train? So So you could state it is something like this. You could see that there is this one wave train and then there's this other wave train. So the it is the intermediate form between the pulse and the continuous wave. And so a wave also have certain things that we have on a oscillatory motion. First of all, it has something which you call as the wavelength. So the wavelength is the peak to peak distance. So you could see from here to here, this is the wavelength lambda. Another thing is the period. The period is the same thing as the one on the oscillatory motion, but instead you want to ask when will it repeat itself after a certain amount of time instead of how many cycles. It is what's the time required for it to repeat itself. That's the period. And also we also have the frequency. Same thing, but obviously the period is the reciprocal of the frequency. So there is something useful that you could gain from all of this intuition. So you know that the wavelength is lambda, and then the period is where the object travels from one spot to the other. So you could state that the velocity of the wave is actually lambda over the period. Or you could write this as the lambda, multiply that by the frequency. So that's something pretty useful for you to actually remember. So we want to start to talk deeply about the mathematics behind wave. So in wave maths, there is one type of wave which I want to talk more deeply about, which is the simple harmonic wave. So this is a sinusoidal type of wave, sine kx minus omega t times a. So in here you could see the omega here is the angular frequency, which I have known that to be 2 pi f. Omega is 2 pi f. And what is this k? The k here is something which you call as the wave number. So basically the wave number tells you about, it is basically the frequency in terms of the distance. And so this is something which you call as the wave number k, which is 2 pi over lambda. So if you actually try to look at this much more carefully, you could see that the v here is actually lambda over f, right? No, sorry, it is lambda f. V is lambda f. So therefore, you could write this to be 2 pi over k, multiply that by omega over 2 pi. So this will be omega over k. And this is the velocity of the wave. So with this, I want to conclude a little bit of the mathematics which describes almost every wave, which I will later try to derive. So it's the partial squared of y over the partial x squared is equal to the 1 over the velocity squared of the partial squared y over the partial t squared. So the units still make sense. And so this basically describes about any type of wave. So the y here is just a function. It could be current, it could be displacement, or many more. But for mechanical waves, you normally deal with this to be about displacements. So we have now already talked about this. So we have already talked about the mathematics behind waves. So now I want to try to actually derive one of the most frequently asked questions, which is about the wave on the string. So we will have a wave which have we will have a string, and the tension is T, and with a linear density of mu. So now the question is, what's the velocity of this wave? So if you actually try to actually do this using dimensional analysis, you would get a very good answer. But how do you justify that answer? So I will dive very deep into the mathematics. So if you don't want to look at the mathematics, you can go ahead and skip into the timestamp below. So let's actually jump into the derivation. So the way that I will try to describe this is by assuming that we will have different particles like like so, and they will have a distance which I will call a at this point. So for each of this distance a, it will be a particle, and they are attached with a with a string, each with a tension of t, and their distance between these guys are a. And so for a arbitrary point, I will say this to be mj, this will be mj minus 1, and this one will be mj plus 1. So there will be some assumptions that I will make. So this will be in the y direction. So first of all, I want to state that the yj will be much more smaller compared to the a. So basically this states that the change in the y wouldn't be so dramatic such that Pythagoras should be applied every time. So with this, you are able to obtain the following. So for the mass j of the particle yj double dot, this will be so here's the thing. I don't want my particle to move in the x direction. So I will just assume those guys to be orthogonally balanced. But for now, I want to try to describe the position in the y direction. So what are the forces inside this mass j? So you could see here that there are two different forces. One of them going in this direction, the other one is going in that direction, each with the magnitude of the t. So let's just actually try to describe this part here. So first, I see that there is an angle here. I will assume that to be theta. So I will call that to be t sine theta. And that will be from the right-hand side. I will call that theta 1. And then from the left-hand side, it will be the same thing. It will be t sine theta 2. And I will just add those two up. So I will obtain here that t, so what's the sine theta? Sine theta is the difference between the height, which will be yj plus 1 minus yj, divided by the hypotenuse, which will be a, since yj is very small compared to a, so we could just assume that to be the case, plus t, and we'll do sine theta 2, which will be yj minus 1 minus yj over a. So anyways, if you actually look at this, maybe you might not agree in the way that I define these two things. And so the way that I actually define those things is by only looking at the image. So why yj minus 1 minus yj instead of yj minus 1? So the simple answer is, if you actually let the yj minus 1 to be bigger compared to yj, I hope that this force would go upwards. But this is not the case. Oh wait, no, sorry. If the yj minus 1 is bigger compared to the yj, the force should go upward, which is the case. So this is the one that I'm hoping for. So with this, we are able to write t over a yj plus 1 minus 2yj plus yj minus 1 over a. No, sorry, that's not there. So that's our differential equation. So you might think that this might be impossible for you to do. Well, it is not truly that impossible, because I would just assume that each of the masses are constant. So I would get the yj here to be t over ma of yj plus 1 minus 2yj plus yj minus 1. So now what? Well, here's the thing that I'm going to be bringing up, which will be diving much more deeper into the mathematics. So if you actually realize here that our physical system has translational symmetry, I will I I will call I will call the translation operator to be s, which is 0 on the diagonal and then 1 above it all. So what this does is that it actually displaces our okay. So the simple way for me to actually to describe this is that if you have the vector y, which has all the positions of the particles, and then you apply a S matrix, this is basically, so if you actually do this for the jth particle, this will be the same thing as you doing it to the j plus 1. No, sorry, that will be equal to the yj plus 1. So that's our hope. So after we have known about this, and then we know that it has this symmetry, we know for a fact that S and this matrix, I will say, which I'll call that to be M of Y. So yeah, this will be Y double dot. So what's the M here? The M is basically T over MA of minus 2, 1, 1 minus 2, 1, 1 minus 2, 1, and etc. So if you actually try to commute these two matrices, you would get 0. So what is this commuting? This basically means that Sm minus Ms is 0. That's basically the case. So basically you know that these two commute. So from here, you would be able to obtain such that as yj would have the eigenvalue beta yj, which will be yj plus 1. So if you actually try to extend this until 0, so basically it's yj plus 1. No, sorry, let's just actually write this to be yj. This is basically equal to beta j of y0. So that's something interesting, is that if you actually let the magnitude of beta to be bigger, not 1, it will later explode between the negative side or the positive side, which is something which we don't really hope within our system. We want it to be controlled within a certain range. So therefore, this is not true, and instead we want the absolute of beta would be 1. This is the one that we are hoping for. So one such solution of this is beta I ka, and I will later explain why do I actually state that the beta is e to the power of I ka. Beta is e to the power I ka. So by knowing this, you would know that the yj plus 1 would be e to the power of I ka of yj, and yj minus 1 is e to the power of negative I ka yj. So plugging it again towards our differential equation here, the one at the top there, you would obtain the yj double dot is equal to t over ma And if you actually look at it up, you can see that this is e to the power of I k a yj minus 2yj plus e to the power negative I k a yj. So you would later obtain this to be t over ma e to the power of I k a plus e to the power of negative I k a over 2 is guaranteed to be cosine ka, which comes from the imaginary parts and the real parts canceling each other out. So you would obtain this to be 2 cosine ka minus 2 yj. And you would later obtain that this is 2t over ma, and then this part of cosine ka minus 1, if you divide it by 2, this will equal to the, oh, sorry. Okay. Yeah. If you actually do this, if this is 1 minus cosine ka, this is actually sine squared ka over 2. So you could write this as the negative, this equals to the negative sine squared ka over 2 yj. So here's something interesting. We do know for a fact that the solution here is negative omega squared. Basically, it doesn't depend on type. And this seems to be very familiar. Because we know the solution of this is guaranteed to be e to the power of I omega t, which we know for a fact. Or basically, you could write this as cosine omega t. So you could just assume that this guy is omega squared. And so we would know what the angular frequency of this entire system. So we would later obtain that the omega squared is 2, sorry, this should be 4 now because of the over 2. So this was 4t over ma sine squared ka over 2. And taking the square root of each, you would be able to obtain omega to be the square root of t over ma sine ka over 2. So we are now approaching to the solution. So if we actually assume a to go to 0, so the distance will be very small, you would notice that this right hand side here will be much more similar to ka over 2. So you would later obtain this to be the square root of t over ta over m. This is equal to the square root of t over mu times k. So this is something which we call as the dispersion relation. So the dispersion relation tells us the angular frequency in terms of the wave number. So this basically describes about your velocity. So you would know your velocity to be omega over k, right? Which is the square root of t over the mass density, mu. And that's the velocity for a wave in a string. So there could be something else for you to actually to describe from here, which is the wave equation itself. So at the top here, I have wrote it down like this. But if you actually pay close attention to the details, you do notice this to be delta squared psi over delta x squared. And so the way that you could actually see this is by actually trying to expand this into some form of limits. Oh, sorry, this is partial squared y over partial x squared times a squared. So technically it's that. So you would be able to obtain the y double dot to be ta over m partial squared y over the partial x squared. So this part here, you could actually expand this to be yj minus 1 minus 2 yj plus yj plus 1. Divide this by a squared. So this is like a Taylor expansion of this partial squared y over the partial x squared. And if you actually look at this again, and then taking a to be near 0, this will be t over mu, partial squared y over partial x squared. This is partial squared y over the partial t squared. And this is the same thing as the partial squared y over the partial t squared equal to the v squared partial squared y over the partial x squared. And that's the wave equation. So you do see now that the wave equation, you could actually get it from mechanical waves. So that's interesting. And also, another thing that I haven't really explained was why did I assume e to the power of ika? Why not something else? Well, the real answer is that if you actually set this guy to be a, and then if you actually apply the translation matrix multiple times, you would get that the multiplication factor would be e to the power of ijka. And the j here tells us about the index. So we know that j times a will later be the position. So this will later transform into e to the power of I kx, which will later tell you the about the wave number straight away by only looking at the equation. So that's about the wave on a string. So we have already talked about the mathematics behind the velocity of a wave for a string. So now we should start to talk about the energy of such wave. So the way that I'll actually try to solve this wave energy problem is to actually try to solve the average power of this wave. And so the way that we actually do this is that we need to first find power. So what's power here? So power is F times V, as as we have already discussed. And here the V is not really the wave, it is not the wave velocity, but it is the particle's velocity, which I will denote that as U. So so with the force and the U here, we will just assume that if we have the wave something like that, and then we are looking at it at this point, and here you would have a angle theta, and then there's a tangent force going that way. So we should be able to obtain that t times sine theta times u would be our solution. So what's u? U is the particle's velocity, and the way that you could actually write this is the partial y over the partial t. And then for the sine theta, if we assume that theta is smaller than 1, we would be able to obtain that the sine theta is approximately the partial y over the partial x. And so what's the y? The y will be a omega cosine, sorry, a cosine omega t minus kx. And so this will be a omega sine omega t minus kx. Is it, no, sorry, it would be negative, I think. Yep. And then for this one, it will be a k sine omega t minus kx. So you can see here that if you actually combine those two together, and yeah, anyways, this would be the negative sign because of certain rules. But yeah, anyways, the power, I am like hoping for this to be positive anyways. So this will be t a squared omega. Oh, sorry. Wait. Yeah, yeah, it's correct. It's t a squared omega k sine squared omega t minus kx. So What about the tension? Do we know about the tension? Well, we last time already figured out about the tensions, which is the square root of t over mu is v. Therefore, we could write t to be mu v squared. So we could just write this as mu v squared, a squared omega k, sine squared omega t minus kx. And another thing is that we know that v times k is omega. So we could still simplify this again into mu v a squared omega squared sine squared omega t minus kx. And this part will later average to be half. So therefore, you would figure out the average power to be half mu a squared omega squared v. That's your average power for a string. So we have already talked about these mechanical waves. So there are some other types of mechanical waves. One of them is sound waves. So sound waves are basically mechanical waves that comes from the vibration of particles. And these are normally longitudinal wave. Longitudinal wave. So we have already talked about mechanical waves for a string. So now there's another type of mechanical waves, which are sound. So sounds are basically vibrations that comes from particles around you. They can they can travel in solids, in liquids, or even in gases. So so now we will actually try to discuss about one particular medium, which is air. So air is a gas. And so if you actually do some physical computations, you would be able to obtain that the V is the square root of gamma P over rho. So P here is pressure, which I will later discuss on the next chapter. Rho is the density, also on the next chapter, that I will fully discuss about density. And also this gamma is the ratio for the heat capacity. So so for air it is the gamma is 7 over 5, but then for other types of materials or gases, they have different gammas. So basically this would later relate to the velocity of air. So so basically if you put the pressure to be 1 atmosphere and then the rho to be air air density, you would be able to obtain the velocity for for the velocity of sound in air, which should be about 343 meters per second. And so another thing about sound waves is that you could actually measure its energy as well. So so last time we have only talked about the the power. And so sometimes it is much more conventional for you to use intensity instead. So let's actually try to discuss first what is intensity. So intensity is basically the power over the area. So basically, you would know that a particle would have a wave. No, sorry. Let's just assume that the particle emits energy across all different directions. It has a constant power. So you could just state that at a particular area, it has a certain intensity, which is the power over the area. So basically the power is spread out, and that is what we call as the intensity. And the unit of intensity is watts per meter squared. So for a spherical type of waves, the intensity is p over 4 pi radius squared. So that's something for you to also to remember. So going back to the sound intensity. So the way that you measure intensity for sound is similar, but for conventional uses, we use a system which uses the unit decibels. So decibels is basically 10 to the log of I over I0, where I0 is 10 to the power of negative 12 watts per meter squared. So this is a relativistic scale that is hearable for us humans, and then you would have thresholds which will correspond to damage to your ear. So this is what we normally use when we discuss about sound intensity or the loudness of the sound. So after we have already talked about sound, I want to talk about certain properties of waves. So first of all, I want to talk about interference. And so what causes interference? Well, it is something which we call as the superposition principle. So the superposition principle tells us that two waves can be summed up together. So using the superposition principle, there could be two types of waves, pairs of waves, I should say. There's constructive and there's this destructive. So constructive basically amplifies amplitude, while destructive actually annihilates. Annihilates. I don't know how to write annihilates. Annihilates. Something like that. Amplitude. So let's just state, for example, if I have this kind of wave, and then I have this kind of wave. This will later be summed up to be a bigger wave. And it is different compared to a destructive wave. Something like that and something like that. You add up together, it'll be a flat line. So that's something for you to consider when you actually deal with interference. There could be some parts in which it will be constructive, there will be some parts in which it will be destructive. And thanks to the superposition principle and with the power of mathematics, we have something which we call as the Fourier analysis, which basically states that any type of wave can be deconstructed into smaller simple harmonic waves that has different amplitudes, which can create different shapes, different waveforms of waves. So the Fourier analysis is sometimes useful for you to use in like signals, in like sounds, and many more. So now going back, we last time have already talked about dispersion. So about dispersion, we have already talked about the dispersion relation, which basically states that the omega transforms with respect to the k, and sometimes it could be in a nonlinear fashion. And so if it is in a nonlinear, if it is nonlinear, it would mean that the velocity would change depending on the frequency or the wave number. So one of the greatest example is the water waves. So this is for a water wave. It is v equal to the square root of lambda g over 2 pi. This is the velocity for waves in deep water. So you could see here that the lambda corresponds to the velocity. It therefore it really depends on the wave number of the wave, which might cause different velocities for the entire waves. So that's something interesting for us to study. So there's also another part that is actually useful for us to understand true interference, which is something called beating. So the way that I'll actually try to describe beating is by taking an example. So let's just state that I have cosine kx minus omega t and cosine k prime of x minus omega t, omega prime t. And I want to note that the omega prime over k prime would be equal to v, same thing as the omega over k. And then you add them both up. They will have the same amplitudes. So what's wrong with this? Well, nothing is truly wrong. And in fact, I will just state that the omega will be added by a certain amount, a little bit, which I will call as the data omega. So by looking at this, so what's cosine plus cosine? So that's the first question that I want to talk about. So by using formulas of the trigonometry, you would be able to obtain that this will equal to 2a cosine kx minus omega t plus k prime x minus omega prime t over 2 cosine kx minus omega t minus k prime x minus omega prime t over 2. That is what you get from the mathematics of cosine plus cosine. So if you see here again, I will just assume omega plus delta omega and then k plus delta k. So we do see that in here, we will just assume that delta omega and delta k is very small. So what we will obtain from the first one will be approximately kx minus omega t, the same thing, but on this side, we could see that it is the difference between the k's and the omega. So I'll just write this as the delta kx plus the delta omega t, the minus over 2. So what do you see here? So basically it is the multiplication of the same wave, but inside it you have a wave with a very small wave number. So if it is a very small wave number, it means it has a very big. Okay, let's just draw it like this. So in here we have the k to be a big number. So that means that the wavelength is very small. So it will be something like this. But then this side here has the wave number to be very small. So it will be something like that. So if you actually multiply both of these things together, you would obtain something like this. So you could see here that there is this big wave and there's these small waves. So this is something that causes beating. So the best way to explain beating is that you would hear the same note, but it will have a sound going loud and then soft, loud and soft. So it will later form like a. So that is beating. And so this is one of the things that music that musicians hear when tuning their instruments. One of them is by hearing the beating of the tuning fork as well as the string. Since since if there's beating, it basically means that the that the frequency is a little bit off. And that is for precision. But obviously you cannot have full precision, right? So therefore, you couldn't truly avoid beating that much. So that's about beating. So after we have talked about beating, we will now talk about nodal lines. So nodal lines are basically if you have two sources and they produce waves, you would later see that there are certain parts in which there are no displacements, and those are called nodal lines. Nodal lines are basically points the in which the particle doesn't displace. And this is caused by the interference, the same idea. So that's about that's the general rule about interference. So now I want to talk a little bit about reflection as well as refraction. So basically, reflection is basically where if you have a wave going to a object, it will later bounce back its energy. So basically, this goes into the conservation of energy. So basically, in here, you cannot really pass through any any energy. So therefore, it is going to be reflected back. But what is refraction? It is basically the same idea. Basically, if you have this guy here and then it goes through a medium, some of them might be refracted into this other medium, while the rest is going to be reflected. And this has to do with the conservation of energy. Same thing. And the easiest way for you to think about this is that if you have a wall, it is not easy for you to carry the momentum towards the wall. But if you have, for example, this guy is a big rope, and while the other side is a thread, you would later see that there will be some of the energy going through the thread while other being bounced back, or maybe the opposite way. There will be a thread going to the big rope, and then some of them will go reflected while the other is going through. So that's the idea about reflection and refraction. So after we have talked about reflection as well as refraction, we can now start to talk a little bit about standing waves. So standing waves are basically a solution of the wave equation for a string. And so basically standing waves are created thanks to boundary conditions. So there are basically two different types of boundaries for standing waves. The first one is a fixed n, while the other is a moving n. So the difference is that for a fixed n, the n here doesn't really displace, while for a loose n or a open n, it can move freely. And so this might cause different types of solutions for the wave equation. So for a standing wave, the general way for you to write it is 2a sine kx sine omega t. But there are only certain solutions for these equations, depending on the omega as well as the k. So there are certain terminologies that I want you to understand when talking about standing waves. So first is that we want to talk about modes or harmonics. So basically, these are basically allowed solutions. So there won't be infinite, so there will be an infinite amount of solutions, but it will be a countable infinite compared to a uncountable infinity, if you already understand about this concept in mathematics. So let's actually talk about certain examples. So let's just state that if I have the wave to have a fixed stand at both ends, therefore I do know certain rules. So first I know that this is a solution, and this is also a solution, and this could also be a solution. And so if you actually look at the pattern, you could see that the first one, let's just assume this has a length of L, the wavelength is actually 2 times the L. And then for the second one, the wavelength is L. For the third one, the wavelength is 2/3 of the length. So we get the knowledge that the length will be m lambda over 2, where the m is a element of the natural number. And so this could also work for other ends, like for a open end, the solution will be something like this, and then something like that, then something like that, and etc. So there can only be a certain amount of solutions for these boundary conditions. So another type of terminology is that there is something which we call as the fundamental mode, which is basically the mode with the largest wavelength. So in here it is 2 times the length. That's the wave. That's the fundamental wave. And then there is overtone, which is the next solution after the prior mode. So for example, the overtone of the fundamental mode is the lambda equals to L. And lastly is that there's something which we call as a node and antinode. So what are those? Nodes are basically points that the displacement is zero, while the antinode is where it is at its max, or the dy over dx is zero. So that's basically the extrema, and this one is the one that doesn't change. So that's the thing about standing waves. So there is something that I missed when talking about standing waves, and one of them is talking about the pipe resonance, in which you would try to describe the wavelength from a tube, and you need to try to describe it for the displacement vectors as well as the uh, pressure vectors. So now I want to try to discuss a little bit about that. For a tube, sorry, for a resonance tube, there are two different kinds of ends. The first one is the closed end, while the other is a open end. So for a closed end, the point at the end, its displacement will be zero. Therefore the displacement is a node, while the pressure is while the change of pressure over the x will be zero. So that means that it is a antinode. While for a open end, the x the partial, oh sorry, let's just call you to be y. Partial y over the partial x will be zero, while the okay, so this would be y, and the partial p over the partial x will be, no, sorry, while the p will be the standard pressure, which will be P0. So that's the atmospheric pressure. So with that, you could actually describe the waves that you would form if you actually look at the open end and the closed end together to form these states like the one on the string. So you are able to figure out what the wavelength is, and then after that you could use the velocity to determine the angular frequency. So that's about the pipe resonance. So now let's go back into the video where I talk about the Doppler effect. So finally, to sum it all up, there is one application that you could use waves, and one of them is from the sound, which we have already described. So I want to talk about the Doppler effect. So so you would know the Doppler effect to be if you have an object moving, you would hear the frequency of the object to be different compared, so it is relative to your viewpoint. So I want to try to derive this as easily as possible. So let's just state that this is you and then this is object. The object is going towards you. So let's just state that it moves at a certain velocity u, and the speed of the wave will be v. So here's the thing. Let's just draw something like this. We would know that the lambda of the so I will give a original wavelength, which will be lambda 0, and then the lambda after, which I will call that as the lambda. So what's the difference between lambda and lambda 0? Well, it has to do with the period. So if you actually do lambda 0 over the period, this will give the next spike, right? Oh, sorry, my bad. So the way that I'll change this from lambda 0 to lambda is that I'll add it by the change of lambda. So what's the change in lambda? So basically, if the object moves closer, this will be a negative sign because the wavelength will be shorter because it is going nearer. So the next peak will be much more nearer. So the change will be decreasing. And then you could use the velocity of the object, which is u, multiply that by t, which is the period. So after the certain amount of time, it will have this next peak. So this is basically like the displacement that I have. So after looking at this, this will be lambda 0 and lambda. So if you actually try to figure out what the frequency is, so the frequency is 1 over the lambda, right? No, sorry. A velocity is lambda times frequency. So therefore, if you do this, v over f, this will equal to the v over f0 minus ut, where f0 is the initial frequency. So if you try to solve for the frequency, we should just, okay, so the t here is basically 1 over frequency, right? So I could just write this down to be the frequency as well of the original one. So we would obtain the new frequency to be f0 over 1 minus u over v. And the minus goes if it is going towards you. And it is positive if it moves away from you. So that's for the moving source. But what about if you are moving instead? Same logic. So let's just state that this is you and this is the object. It is, so you are going in that direction. And there are lambdas. So same idea. Let's just state that within the time period t, you are moving u, this is going to be the change in the lambda. Or basically, it's the uh, lambda 0 minus lambda. We will use the same logic. So let's just actually go and write it all down. This will be u over the frequency. This will equal to the lambda 0 is guaranteed to be v over f minus f0, sorry. And then the lambda here is the one that's heard. That will be the v over the f. So if we try to discover what the f is u plus v times f0 over v. So it's 1 plus u over v f0. And so it is positive if you are moving towards the object. And so you could actually combine these two things together. So it will be like a 1 plus minus u over v over 1 minus u over v plus or minus u over v of the f0. But you need to remember which one is the positive side, which one is the negative side. So that's something that you need to observe. So this is of the observer, this is the source. So that's a way for you to actually to describe the Doppler effect. So there is also another thing, is that if you actually move faster than the velocity of the wave, you could have something which we call as a shock wave. So basically the object moves faster compared to the speed. And so this might cause something like this. This is like a Doppler effect, but the source is moving much more faster compared to the velocity of the wave. And this will cause something which we call as a shock wave or a sonic boom. So the way that you actually describe a sonic boom, okay, so first of all, in here I draw lines. This is basically the velocity of the wave, and then this is the velocity of the object. So there are two things for you to describe the sonic boom or the shock wave. First is that you could actually know the Mach number. So the Mach number basically states the velocity of the object divided by the velocity of the wave. This is the Mach number. While the Mach angle corresponds to the cone angle. So basically it is this angle here, theta. So this angle here is something which you call as the Mach angle. So just by only using these two things, you could actually determine the velocity. No, sorry. You could determine your height thanks to a sonic boom if you know the velocity of the wave as well as the velocity of the object. So that's all for wave motion. So I hope this really helps. And if there are any if there is any questions, please leave it in the comments. And if you want more of these videos, please consider subscribing as well as liking the videos. So thank you very much, and I will see you on the next episode.